Hello everyone. Today we are going to talk about the particle filter. Particle filter. This is a special kind of filter to estimate the system dynamics or the model parameters based on or coming from the measurements. Okay? And so we should write this explanation in here. The particle filter, simply PF, or it's called the sequential Monte Carlo method. SMC, okay, is a powerful tool to estimate dynamic system, which especially for the that includes the nonlinearity and non-Gaussian noise. This is important because in the Kalman filter we have considered that this is a Gaussian noise, but the particle filter uses probabilistic technique to assign the coefficients for each particle, and it eliminates the non-Gaussian noises. Okay, but in order to understand that, we need to understand another topics. PF, we must study of the first of all, the Bayesian estimation method. This is the base of everything in the probability, and after that we need to talk about the sequential importance sampling. This is also another important topic about the eliminating noise from the measurement. Okay, and after that we need to talk about the importance of sampling. This is different from the two. Okay, and after that we will build the Monte Carlo method, but just Monte Carlo, not the sequential one. After that we will talk about the resampling techniques to build to particle filter. Okay, this 5 list contains or creates the R particle filter nomination, or the basis of this algorithm. Okay, and so let's start with the Bayesian estimation. In this case, we need to define it. It is a statistical method for estimating posterior probability, which means that the last probability for a given any condition in the probability theory. In the Turkish, this is the sonsal olasılık. Okay, and so this is based on how we can calculate it. Firstly, we need to utilize the conditional and marginal probability. Okay, so this is important, and also this is important concepts. Okay, and so how we can define that? Firstly, we need to write the pxy probability rate, which is equals to the pyx times px and py. Okay, this is the Bayesian rule. To what? For a given y, we can conclude that we will calculate to the what the probability rate of the x, but for a given y. And so if we know this feature, and then we can turn into the what the yx or xy. This is convertible. Okay, and so first of all, this is equals to the what? Marginal likelihood in terms of the what? The existence probability for a given condition. For example, if we have any 10 numbers in here, we know that we have 10 numbers, but they could be 100s. Okay, and so if we want to only know to what for a given 10 number probability at what 100s, they are both the x values, but only we will focus on these times, and so this is equals to what is 0.1. Okay, and so the other important probability is that the prior probability is this, because we want to know the probability of the x for a given y, and so this is called also the marginal likelihood, but we call it to the what? A prior probability. For example, if we have any knowledge about the rain or Sunday, for example, if we know that these two conditions are happen in the what? In a day, and so this is equals to what? The 0.5 and 0.5. But if we know that other three conditions can happen in a day, and so this is equals to what? 0.2. This is the happening rate for a given prior information about the what? Our probability. Okay, and so this is called the likelihood. In Turkish, benzeşim. Okay, and so generally we assign the model to this term in order to calculate the R probability rate in this nomination. But how we can analyze this condition? Let's create an example just like this one. You have a coin and you want to estimate theta value of it, but this is representing to what? Landing heads. Okay, and so 10 times tossing gives us to what? 7 heads, and we have 3 tails in here. We know that this is the prior information, and we want to estimate the what? The theta values of it landing heads in here. But how we can do that? Normally you can say that the probability rate of the what? The 7 in here normally, but it's not like that. We should use the what? The Bayesian estimation. And so in order to do that, just remember what to define prior probability. Which means that assume uniform prior R theta into what? 0 and 1. We may have the 0 and 1 in here, and so if we tossing the coin, and so either we will have the 0 and 1, which means that we can write this probability p theta is equals to the 1 for a given what? 0, theta, and 1. This is the hat, for example, this is the coin, and so we know that there always be a head and tails, which means that we have one value, 100% value to what? To this happening rate in this prior probability. Okay, this is so simple. So after that, we need to define the likelihood function. So the likelihood of 7 heads in 10 tosses can be given by P data theta is equals to what? 10 and 7. This is a combinator value. Theta 7, 1 minus theta over 3. Because one of them is 0, one of them is 1. And so this can be written just like that. Okay? And so this is called the beta distribution. We know it from the literature. Okay? And after that, if we have these informations, and then we will continue with the computing the posterior probability. Using the bias rule, we get P theta data. For a given 0 and 1 condition, we can write it P data and theta. This is likelihood, and P theta and also P data. This is equals to the what? 1 theta over 3. Because it's 1, and so the presence values of the head and coin or tossing values is also 1, and so we can assign it to this value. And then we can write that this probability is equals to the what? Beta distribution of theta alpha 8 beta 4. Okay, this is a prior knowledge about the beta distribution. You need to look at the beta, and so in order to find these values, we can model it based on these conditions. Okay, so this is utilized to what? The 0 and 1 condition probability distributions in the theory of the probability. And so after that, we need to turn into the posterior mean value, which is the mean value of beta distribution directly represents to the what? To our chance to getting 7 heads and 3 tails. And so this can easily be calculated by the expected value alpha plus beta. This is coming from this one, but this is coming from this one. Okay, and so 8 and 12, and so 3.3 divided by 2 is given in here. But normally you can say that the 7 and 10 for this distribution, but it's not. For obtaining to what? To theta of it landing heads probability for a given 10 times tossing, it's the measurement values of what? The 7 gives us 3 divided by 3, 3 divided by 2 divided by 3 chance, or 66% chance to happen this event. Okay, see, for this distribution we can say that this is the mean value of the what? Our chance to what? Taking the head in this distribution. Okay, and so if we know this information, and then we will take a tossing a coin, and so we will expect that to what? The 66% chance to what? To taking head values. Okay, and so in the next lesson I will study or I will build the MATLAB example session about it. Okay?